Okay, so today I'm going to be talking about the Lithosphere-Asthenosphere boundary beneath hotspots. And we're really interested, as you heard in the last talk, about the Lithosphere-Asthenosphere boundary beneath the oceanic lithosphere, since it has a relatively simple and short history in comparison to the continents, and it should have a relatively simple age depth trend. But as you can see here in the bottom right-hand corner, looking at some global comparisons of constraints on this discontinuity, there is not a simple age-depth relationship that's emerged. And so what we'd like to do is to look at this boundary using the in situ constraints that we can get from these very special places, hotspots. As you can see here in the colored areas within the oceanic plates, these are some of our best in situ measurements, besides ocean bottom instruments, obviously. And you might say, well, hotspots are a really strange place to look, since they're an anomalous region in terms of the entire oceanic plate. But the other way to look at it is that they're actually the ideal place to consider the mechanism that defines the lithosphere-asthenosphere boundary, since we predict different characteristics for the lithosphere-asthenosphere boundary depending on how that LAB is defined. So for instance, if the plate is thermally defined, we might expect that a thermal anomaly rising from below would heat the lid and necessarily thin it. Whereas if the plate is defined by composition, you might expect that a rising thermal anomaly would either upwarp it without thinning or actually add material to it, making it thicker by the addition of compositionally buoyant material. And so we can use these predictions to look at what mechanism is defining the lid beneath hotspot regions. And of course, we're also very interested in what hotspots can tell us about the asthenosphere beneath them. For instance, is there partial melting? We've heard a lot about that already. Is there partial melting that exists perhaps along a permeability boundary that is moving towards a volcanic area? Is there partial melting in some kind of melt triangle region? Or does partial melting exist ubiquitously or just in these very discrete locations beneath ocean islands? Is the partial melt aligned? Of course, that might be really important. And as we know, anisotropy is a very important aspect of the lithosphere-asthenosphere boundary and composition as well. And if there is melt beneath an area such as a hotspot, we're also very interested in the character of that melt and how it persists in depth. So is it a very gradual transition, like has been suggested by these models of Pacific transects, or is there some kind of sharper boundary, as has been suggested by some receiver function studies in the past beneath Hawaii? And the other thing I'm going to be looking into a bit today is where the actual plume or hotspot is located beneath the hotspot, since it might, it seems straightforward that it would be right beneath the hotspot, but that's not always the case, and it's really important to our understanding of how the hotspot is interacting with the plate and what defines the plate. So that will be another thing I'll be looking into. Today I'm going to be looking at receiver functions, where I rotate the recorded waveform into its P and S components, and I'm going to be looking using two methods. One is to bin by conversion point before deconvolving and simultaneously migrating in depth in 1D. And the other method that I'll be using is to look using a an extended multi-taper receiver function method. That's very good because it's stable for single waveforms, and then we can get a more 3D picture of a given region. And I'll just point out the S to P wave is the one I'm going to be focusing on today, a shear wave that converts to a P wave before reaching the seismic station. And I'm going to focus on 4 hotspots that I've been looking at recently: Hawaii, Galapagos, Iceland, and Afar. I'm going to start with Afar. So The far region is a bit different, since it's a place where continental rifting is actually transitioning to oceanic spreading. And here you can see just the triple junction region. The boundary faults are outlined in black, and you can see the areas of quaternary volcanism in red. The youngest arm of the rift is the main Ethiopian rift in the south, and flood basalt volcanism last occurred here about 30 million years ago. So in afar, the first thing that we saw looking at the receiver functions was that there was a huge variation in the character of these waveforms as we moved from flank to rift. And you can see that on the figures on the right-hand side. At about 75 kilometers depth, we have a strong negative at about 75 kilometers depth. And beneath the rift itself, we saw no evidence of that strong phase. Instead, we saw, if anything, a very subtle positive phase at similar depths. And when I plot the polarity of significant phases in that depth range on the map here, you can see that as the red and the blue, all negative phases or velocity decreases are shown in red, and velocity increases are shown, in blue, and velocity increases are shown in red. And you can see that there's a pretty strong correlation with the tectonics of the region. So that's quite exciting. We think that velocity decrease is representing the base of the lithosphere on the flank, whereas beneath the rift itself, we must be seeing something completely different. We'll have to do some modeling in a bit to talk about what that actually is, but it's likely related to the base of a slow area, probably caused by a small amount of partial melting. We can use this other method, the extended multi-taper, to look at this in 3D. So now looking at a cross-section running along the flank from south to north, you can see we see a MOHO phase and then a phase that we associate with the Lithosphere-Asthenosphere boundary, shallowing slightly in the middle of that transect where flood basalt volcanism has likely occurred, or occurred about 30 million years ago. And then as we move across the rift from flank to rift, as you can see here, moving from B to B prime, you can see that there is a lithosphere-asthenosphere boundary phase on the flank of the rift, and then a sharp transition to an area where we see nothing but a subtle positive polarity phase. And the same thing is true in the south. We see a lithosphere-asthenosphere boundary phase on the flank, and only a positive phase beneath the rift itself. And we've done some modeling to constrain the velocity gradients associated with those transitions. And what we find is that there's a very strong velocity decrease with depth in the flank. It's likely defined by a small amount of partial melting beneath it. And beneath the rift, we have this very subtle positive phase. It's actually very difficult to match without putting in a pretty strong, about 12% over 20 kilometers depth velocity increase with depth. And so we think that there's a small amount of partial melting that occurs above that discontinuity. And we've done some really simple geodynamic models to constrain what kind of situation can really explain those velocity gradients that we saw. And our best fitting model was one where we had a potential temperature of about 1350 to 1400 degrees. That gives you a velocity increase with depth at about 60 to 80 kilometers. And a moderate amount of melt retention will give you this kind of velocity increase with depth at the onset of melting. And that depth is quite shallow, and it implies that there's probably not a really strong plume influence directly beneath where we're looking. And if there is one at all, it must be just off of where we're looking, perhaps a little bit further to the south. I can show you why I think that. This is just some comparisons with some previous work. We're in pretty good agreement, actually, with previous receiver functions and joint receiver function surface waves that find a velocity decrease with depth in the flank and a velocity increase beneath the rift itself. This is some brand new surface wave results from Ryan Gallagher, and I encourage you to go to his poster where you can talk more about surface wave results from this region. But what Ryan found is that there's evidence for slow velocities very shallow throughout the rift. And here in the south, beneath the main Ethiopian rift where I was looking, you see things that are slow down to about 50 kilometers, but not very much deeper, except for just south of AA prime, where you see this kind of slow anomaly going much deeper into the mantle, which could indicate where this kind of deep hot welling might be, upwelling might be coming up. So beneath the far, we found a sharp boundary at the base of the lithosphere on the flank of the rift, but then beneath the rift itself, we saw nothing but a velocity increase that we think is related to the onset of melting. And this transition from the flank to the rift is actually quite abrupt. It can't be defined thermally, otherwise you would see something approximating this kind of a thermal boundary, something shallowing very, very gradually with depth, and that's not what we saw at all. So we think that there's some kind of compositional definition to the lid, and that the lid itself may be destroyed in some way beneath the rift itself. So we'd like to look somewhere where we know that a plume actually exists, rather than being maybe just off of where we're looking. And so to do that, we've also looked at Hawaii. I looked at the plume experiment, which was about 70 seafloor instruments and 10 land stations deployed around the island of Hawaii. This is a classic example of hotspot volcanism with plate motion over a fixed plume. And these models that have been developed for mechanisms to define the plate, and also to help us understand what supports the topographic swell above Hawaii, have been developed for Hawaii. And I'll just remind you that beneath Hawaii, the heat flow measurements are quite low, and they suggest that the plate is not purely thermally defined. Otherwise, you'd see a much greater heat flow anomaly. So the swell must be supported by some other mechanism. And so beneath Hawaii, what we found, looking along the island chain from A to A prime, was certainly a MOHO phase, that's the red phase up here, and then we found a Lithosphere-Asthenosphere boundary phase beneath the main island. Evidence for this is a little bit weaker as you move towards A, and I'll talk a bit more about resolution towards the end of this talk and whether or not that's well resolved, kind of this LAB phase disappearing. We also saw an LAB phase pretty strongly just west of the main island and east of it, as you can see here. We also found this red phase, again, a velocity increase with depth at about 110 kilometers at its thinnest. It's about 125 kilometers in the well-resolved region close to the island, and then it gets down to about 155 kilometers, just 100 kilometers west of the main island. This phase, we think, is again associated with the onset of melting. It's much deeper than anything we saw in afar. The location where it gets much deeper is perfectly aligned with the slowest anomaly from the surface waves. As you can see here, these surface wave contours are shown by the gray and black contours. And so we think that this is actually where the plume is upwelling just west of the island of Hawaii. And there's a small amount of variation in terms of the depth of the Lithosphere-Asthenosphere boundary. It's about 93 kilometers over here. It's shallowest to the shallowest point, probably at about 75 kilometers. It's not a huge variation. And this break is also somewhat in question in terms of whether or not that's resolved as actually disappearing. But I will point out that even if it is an LAB that's not present there, and that perhaps the gradient is actually very gradual, and so we're not able to see it with these receiver functions, even if that's the case, the area that it's actually missing is quite small. So certainly can't be purely thermally defined. It probably needs some kind of to be destroyed by some kind of the lid itself maybe needs to be defined compositionally, or some kind of diking needs to exist to kind of get this abrupt transition from an LAB to not one. So we've done some modeling to constrain the velocities that must be associated with the observed waveforms, and we found that we actually do need a pretty strong, sharp velocity decrease beneath the area where we think the plume is upwelling, just to the west of Hawaii. And then we need a pretty strong velocity increase as well at the base of that plume, that melting. And so we also have done some really, really simple geodynamic models to see what kind of mechanism can help us explain these observations in Hawaii. And what we found is that a purely thermal model, as you can see here by these dashed lines in the background, cannot define what we see. We need this kind of small amount of partial melting in this area here to give us a velocity decrease with depth and then a velocity increase. And these, the blue line here is for the plume pancake region, which we think is about 1450 degrees potential temperature. You need something like 1550 degrees in the actual location of the plume to give you that deeper velocity increase with depth. And so how does this compare to other well-known receiver function results in the area? Well, overall, it's actually in pretty good agreement. This paper from Lee et al. Found an LAB that was about 100 kilometers beneath the main island of Hawaii. They were using just the land stations, and they saw shallowing towards the northwest, which I said before. It's not really clear whether it's a resolution issue or whether, for me, or whether the LAB is actually disappearing. I'm not, so the agreement with that is more tenuous. But if you compare to their PS receiver function result, which is a little bit earlier, you see they had a velocity increase with depth that was really strong and sharp at really similar depths to what I'm seeing. So if it's visible by PS, it means also that it must be very strong and sharp, since PS is, of course, higher frequency. And so the other thing is that it was really shocking to find this plume at about 100 kilometers west of Hawaii. And so what does this mean about where the plume actually is in depth? And to look at this a little more, I'll talk about some other constraints. So it's been suggested that the plume is approximately 200 kilometers southwest of Hawaii based on receiver function results from the transition zone. And or an alternative is that it's actually located here about 700 kilometers away before reaching the island. And so it's possible that the plume is approaching kind of from a westward approach. The other possibility is that the plume is located exactly beneath the island, as has been suggested by recent body wave tomography. So as you can see here, we can't really distinguish between these two, but if the plume is approaching from the west, that's fine. It needs to actually, the material does need to reach the island axis at some point, so it does need to be guided, perhaps along some kind of permeability boundary at the Lithosphere-Asthenosphere boundary. If the plume is rising directly from below, then we suggest it must be diverted somehow by a resistive route that possibly formed during the large melting event that actually caused the island of Hawaii before the melt actually reaches the island axis. And so going back to that resolution issue, we've been looking into this a bit more because we'd really like to put some tighter constraints. And this is really preliminary, so I won't go on about this, but it's what I'd like to do a lot more in the future. We wanted to know, first of all, whether we can resolve these very complicated structures that we claim that we're seeing. In fact, we put in a synthetic model that looks like the model we expect, a lithosphere-asthenosphere boundary, the onset of melting, deepening just west of the main island, and then thinning again. And we found that we were able to resolve this structure actually quite well using full waveform tomography, or full waveform modeling, sorry. And one interesting thing about this is that right in this area, it's a little bit hard to see in the slide, but this amplitude does get slightly lower. And so it could be that this is an artifact of a bit of defocusing caused by these strong lateral variations that exist in Hawaii. So we'd like to do more of this and more in-depth constraints looking at this kind of thing in the future. And now I'd just like to bring you through some of my most recent results looking at Galapagos. Here we're looking at the Signet array, which is this group of stations that were deployed here in Isabella, and also using station PAYG in green. This is very young oceanic lithosphere, and it's a really interesting place since we can look at the interaction between a hotspot and a ridge. So beneath Galapagos, we see a moho throughout. We see a blue phase, which is this lithosphere-asthenosphere boundary phase. It's slightly, seems to split here as you move towards the east. And when I compare this, it actually compares really well to the surface wave results from the region that found a thicker lid to the west and a thinner lid to the east. So if we compare to that, then this is probably the LAB here, thinning towards the east. And the other thing that we saw throughout the region was this deep red phase. It's at the edge of our resolution, but it seems to get much deeper. In every case, it gets deeper beneath where we have this very slow velocity anomaly at 75 kilometers depth. It's 3.9 in the surface wave result. And every time that very slow velocity exists, the receiver function realization of that phase we think is the onset of melting gets much deeper. You can see that here and here. And so we've done some modeling. This is the data from station PAYG to show that basically this phase at depth is required. We need a velocity increase with depth throughout the region. Here we have approximately 130 kilometers depth. The LAB phase, it can actually exist as a small sharp gradient, or it can exist as a relatively gradual. It's a gradual gradient, which is the green line behind that red one. Yeah. So it's relatively unconstrained how sharp that gradient is, and that could be because of lateral variations, as the surface wave saw across the region. Since this is a stack of all the data from PAYG, which is a pretty big area, it could be that the gradient is actually quite gradual, and so that question still exists, unfortunately, beneath the Galapagos. And this is just to show you what the surface wave saw. They saw a lid that was slightly deeper to the west than in the east. And so when I plot my results up against the surface waves, just in a lateral view, you can see that the lid is much thicker towards the south, or a little bit thicker towards the southwest in comparison to the northeast. And the location of the plume impingement at the transition zone is about just southwest of Isabella. And that's the location where the surface waves found this very strong velocity anomaly that I showed you at 75 kilometers depth. That's outlined by the dashed line here. And then they found another anomaly in the northeast. And so they thought that, based on the transition zone, they thought that this is actually the plume, and then it's coming up and interacting with the ridge up here. And so when you compare to the region that I see the deepest realization of the onset of melting, you can see that here in the red regions. It's actually in pretty good agreement. I see shallower depths for that phase everywhere except for the regions where the surface waves have the slowest velocities. And finally, just some results that are really new from Iceland. Here, I divided the data into a southern conversion point bin and a northern one. And I found in the north that I have a moho. And the next most important thing is probably this strong velocity increase with depth at about, here it must be about 140 or 150 kilometers depth. And in the south, we saw a strong moho, a strong LAB, but then a very subtle phase. I'm not certain how well resolved this is at all right now, but a very subtle phase at about 100 kilometers, so much shallower. So we think that the plume is having a stronger influence in the north. And you can see this in the multi-taper as well. Let's see. So first of all, you can see this LAB phase throughout, and you can see moving along 3, you see an onset of melting phase at about 100 kilometers. It gets much deeper as you move to the east, and then it gets much deeper as you move to the northeast as well along 4. And you can compare this to both surface waves from Lee and Dietrich, and also the older ice melt results from Richard Allen show a similar thing with relatively fast velocities beneath the island itself and slow velocities in the north. My phase is, you can see here, it's deepest just to the northeast, but that's probably just outside of the region of resolution for this. So I think it's actually relatively well agreement that there's something in the northeast for the plume. And the LAB is at a relatively constant depth, although slightly deeper towards the northeast as well. And so the whole point of this is to make some comparisons among these Unfortunately, many of them are at very young age seafloor or at the transition to seafloor. But overall, what I see is pretty consistent results for a phase associated with the lithosphere-asthenosphere boundary, something in the depth range of, say, 50 to 80 kilometers, with subtle variations within each region, actually. In terms of sharpness, there's a lot of places that are not well constrained. I haven't done it in Iceland. Galapagos could be quite gradual, or that could be caused by lateral variations. Beneath the Far, we had a very sharp gradient, but it was off-axis. Beneath the rift itself, we didn't see any evidence for lithosphere-asthenosphere boundary phase. Beneath Hawaii, we did have a strong gradient. And the onset of melting, again, there's not really a big correlation besides the fact that beneath the Far, we saw a relatively shallow phase, and in the rest of these places, we saw something at about 125 to 160 kilometers. So in summary, what we can say is that beneath the Far, we think that the mantle lithosphere might be destroyed. We don't see a lithosphere-asthenosphere boundary phase. But in all of these oceanic places, we do see evidence for lithosphere-asthenosphere boundary. I also point out that beneath Hawaii, we were really shocked to see the plume off-axis just west of the main island. Although, of course, many others had seen it off-axis at much deeper depths. But in these other locations, it may be slightly less shocking, but in fact, in all of the cases, the plume is never located for us directly beneath the island itself. It seems to be consistently just off-axis in Galapagos, just southwest of the main island, which is relatively consistent with the plate motion. Hawaii and Iceland, not as much, but Iceland we saw something just to the northeast. And that's right, besides the plume being off-axis, the lithosphere-asthenosphere boundary was consistently thicker. I don't know if you noticed, but it was consistently thicker exactly in the location where we had the plume impingement. So beneath Hawaii, it was about 90 kilometers just west of the main island, and Galapagos as well. It was slightly thicker on the western edge of the island, and beneath Iceland, slightly thicker in the northeast. So that would suggest some kind of compositional component, especially because we're not observing the predicted thinning that you would expect for a thermally defined lid. So in conclusion, a sharp rigid lid is imaged on the flank of the Afar Rift. No mantle lid exists beneath the rift itself, rather a discontinuity at the onset of melting, which we associate with decompression melting without a strong plume influence. The base of a melt-rich layer was imaged beneath Hawaii, Galapagos, and Iceland, increasing in depth where the plume impinges on the lithosphere, although in all cases it's off-axis. The lithosphere-asthenosphere boundary is deep, near the region of plume impingement, and that's consistent with a compositional definition for the lid. Melt might be guided towards the axis of volcanism, or it needs to be, by some kind of pre-existing structures, and it suggests that melt is retained in the asthenosphere beneath areas of active volcanism in sufficient quantities and over significant depth ranges to be observed seismically. Thanks.